All right, hello everybody. This is the point that we stopped last week. So I was showing you the influence of the energy of the intermediate in an inorganic substitution reaction. And we discussed together that depending on the energy of the intermediate relative to the starting complex, the reaction would be thermodynamically favored or not. So the way to compare the energy to have a rough idea about the relative energies is using the ligand field stabilization energy. Here we are comparing in absolute numbers, and we always compare between the coordination number 6 and the coordination number 7 or the coordination number 5. Okay, so coordination number 7 if the reaction goes through an associative mechanism, and coordination number 5 if it goes through a dissociative mechanism. So for the D1 case, the ligand field stabilization energy is 4, and for the coordination number 7 is 5.28, and coordination number 6 is 4.57. Okay, so that means any of the intermediates are more stable than the starting complex. Therefore, D1 complexes, they tend to be labile. Okay, they tend to react kind of fast. And the same goes for the D2. So here the intermediate states are more stable than the octahedral complex, therefore the compound is labile. However, for the D3 case, the octahedral geometry is more stable than the coordination number 7 intermediate or coordination number 5. Therefore, D3 complexes, they tend to be inert. So, of course, that this is not always true. So there will be some exceptions, but this will explain most of the cases. Okay, so just looking at the relative energy of the starting compound and the intermediates, you can have an idea about if the complex is labile or inert based on the d electrons. Just the d configuration will tell you about that. Okay, so let's move on. For today, I would like to talk about the D4 configurations, because D4 is a little more tricky than D1, D2, and D3. So we are going to see two different cases here. So let's start here with the most simple case. So when we have 4 electrons in an octahedral ligand field or octahedral geometry, remember this is the T2G group and this is the EG group. So there are two different ways to fill the T2G and EG orbitals. So let's start doing that. 1, 2, 3. The fourth electron can either be paired or go up. It will be paired when the gap is too high, and it will go up when the gap is small. So let's start pairing the electron here down in the T2G group. Okay? And let's calculate the ligand field stabilization energy. And in this case, I will ignore the pairing energy, and there is a reason for that I will explain to you in few minutes. Okay, So ligand field stabilization energy for this case over here. We have 1, 2, 3, 4 electrons, and they are being stabilized by a factor of 4. Therefore, the total ligand field stabilization energy is going to be minus 60. Okay. All right. So now let's take a look at the intermediates. So coordination number 7, if the reaction goes through an associative mechanism. So now let's move these 4 electrons in this configuration. So we are going to do 1, 2, 3, and 4. So why did I do 1, 2, 3, and 4 back here and not 1, 2, 3, and 4 over there? Because the 4 electrons belongs to dxz, dyz, and dxy orbitals. So these 4 electrons must be in dxz, dyz, and dxy orbitals. That's why I moved the 4th electron back here and not over there, okay? So now let's calculate the ligand field stabilization energy. 1, 2, 3 electrons being stabilized by a factor of 5.28, and 1 electron being destabilized by a factor of 2.82. So that's a ligand field stabilization energy of minus 13. Okay. Okay, and let's do the same thing, but now going through a dissociative mechanism, generating an intermediate with coordination number 5. So I'm going to do the same thing here. We have 4 electrons that belongs to the dxz, dyz, and dxy orbitals, and they will have to be transported to this electronic configuration. So let's go 1, 2, 3, and 4. Okay, so the same idea here. They belong to dxz, dyz, and dxy orbitals. That's why they have to be in these 2 groups over here. 1, 2, 3, and 4. And let's calculate the ligand field stabilization energy, again in this case. So we have 1, 2, 3 electrons being stabilized by a factor of 4.57, and 1 electron being stabilized by a factor of 0.86. So that's a total ligand field stabilization of 14.6. And let's make a note here that this is a low spin complex. All right. Okay, now what we have to do is to compare the ligand field stabilization energy for the octahedral complex with the 2 possible intermediates. If the compound's more stabilized in a coordination number 7 or 5, this complex will be labile. If not, the complex does not have any motivation to react, and therefore it will be inert. one detail here about the pairing energy. Can you see here that I have one pairing energy in the initial state and in both of the intermediate states? So therefore, just for comparison, we do not include the pairing energy because they will be the same in the beginning and in any of the intermediates. So just the energy here of the electrons is enough for the comparison. As you can see here, the starting compound, the octahedral geometry, is stabilized by a factor of 16. The coordination number 7 intermediate is stabilized by a factor of 13. And the coordination number 5 intermediate is stabilized by a factor of 14.6. What does that mean? It means that the octahedral complex is the most stable between the three. Therefore, there is no energetic motivation for the system to go to any of the intermediates. So the system is happy where it is, which means that D4 low spin complexes are inert. Okay, because the octahedral geometry is the most stable between the three. Okay, so the low spin is one of the two possibilities. So now let's investigate the high spin configuration and let's see if D4 high spin complexes are inert or labile. Okay, so let me move this a little bit up. Okay, so you can see here. So I will cover here just to avoid any confusion. And let's do the same thing. Now, 4 electrons, 1, 2, 3, in a high spin configuration. So that means 1 electron goes all the way up there. Okay, so now we have 3 electrons in the T2G group and 1 electron that belongs to the EG group. Attention with that. So now we are talking here about D4 configuration and high spin. Okay, same thing, guys. Let's calculate the ligand field stabilization energy for the octahedral configuration. So we have here 1, 2, 3 electrons being stabilized by a factor of 4. And 1 electron being destabilized by a factor of 6. Therefore, the ligand field stabilization energy is -6. Now let's move these 4 electrons to a coordination number 7 intermediate. So we have 3 electrons in the T2G orbitals, 1, 2, 3, and now we have 1 electron in the EG configuration. See the difference over here? So now this electron has to go to either a dz squared or a dx squared minus y squared. Looking at the system, the dx squared has lower energy than the dz squared, so it will be filled first. So that's the configuration that we are going to get. And here we do the same thing. Calculate the ligand field stabilization energy. 2 electrons are being stabilized by a factor of 5.28, and 2 electrons being destabilized by a factor of 2.82. So that means the ligand field stabilization energy is 4.92, okay? Or the system is being stabilized by a 4.92 units. Okay. So this is not the only possibility. So there is the other side, coordination number 5. So let's see if this configuration will be more or less stable than the octahedral one. Again, 1, 2, 3 electrons that belongs to the T2G group. So they have to be moved here to the T2G orbitals, or the DXZ, DYZ, and DXY. So 1, 2, and 3. And 1 electron that belongs to the dz squared and dx squared minus y squared. So now let's take a look here at this system. And as you can see, the dz squared orbital has lower energy than the dx squared minus y squared. Therefore, it will be the first one to be filled. Okay, and we do the same thing here. 1, 2 electrons being stabilized by a factor of 4.57, and 1 electron being stabilized by a factor of 0.86, and 1 electron destabilizing the system by a factor of 0.86. That's going to give a ligand field stabilization energy of 9.14. All right. Next step. Now we have to compare the octahedral geometry ligand field stabilization energy with the other two possibilities. If at least one of them is more stable than the start, that means the complex will be labile. If not, it will be inert. Ligand field stabilization energy for the octahedral geometry is 6. For coordination number 7 is 4.92. So this is not going to happen. So there is no motivation to move from the coordination number 6 to coordination number 7. However, if we take a look at the coordination number 5, the ligand field stabilization energy is higher than the octahedral geometry, than the coordination number 6. Therefore, there is a strong motivation to move towards this more stable state. So this intermediate is super stable. Therefore, the complex will undergo some sort of reaction, and when that happens, we call the complex labile. Okay? It doesn't mean the mechanism is going to be exclusively dissociative, but the possibility for that to happen is very strong. Okay? So that's how we are going to use the ligand field stabilization energy to decide if a d electron configuration is labile or inert. Okay? So let me know if you have any questions. I will be happy to answer that for you. Don't forget that we have office hours tomorrow on Tuesday, and don't forget that we have the exam on Friday. Okay? So I will finish this part right now, and then I will move back to the computer.